Okay, so in this video we're going to look at enlargement, which is also known as dilation. And the first thing to say about enlargement is it can be about making things larger, but it can equally be about shrinking things down. So let's go ahead and do an enlargement without any marks at all on the coordinate plane. So we've just got a set of axes here, and I'm going to run an animation so you can see the whole plane and all of the points on the plane enlarging, just so that we know what we're dealing with before we actually go ahead and enlarge some lines maybe and object shapes. Okay, so let's start. I'm going to start by expanding from the origin, and it will be as if I'm just pulling it out from that 0, 0 coordinates. Okay, so like this, until it's, let's say, 3 times bigger. So we'll stop at 3 times bigger. So what we've done is we've expanded by a scale factor of 3 from the origin at 0, 0. Okay, now I'm going to rerun the animation, but this time what I want you to do is focus on this square here. Now what happens exactly to that square? So let's keep our cursor over it, run the animation, and you can see two things are happening really. The obvious one is that it gets bigger, but equally obvious is that it moves. Okay, so the only time when an enlargement won't move, it just expands, it just gets bigger or smaller. The only time when that happens is when the center of enlargement is right over, in fact, in the middle of the object. However, for lots of situations, that's not going to be the case, so we expect a movement as well as the expansion, the enlargement or the contraction, the shrinking down. So let's go ahead and draw around our square then, to mark it out. And now what we're going to do is consider, well, how do I find out what the coordinates are for the enlarged image? So we call this the object. We're now going to try and plot out the image. Well, if you're expanding, or enlarging I should say, from the origin, then you can work with a method that I'm going to show you now, which is simply scaling up the coordinates. If that's not the case, if the center of enlargement isn't here, we're going to have to use another method. But we're going to start by that simple method. So first of all, let's identify what the coordinates are. So let's mark them, A, B, C, and D. And we can see that A, for example, is at 7, 1. B is at 7, 0. C is at 8, 0. And D is at 8, 1. So if we ask ourselves to start with about A and its image, let's call it A prime, it's going to be over here somewhere. Let's start with the x-coordinate of A. Well, the x-coordinate of A is 7. So the x-coordinate of the image, I'm going to write it like that, is going to be 3 times the x-coordinate of the object. Well, the x-coordinate of the object we've said is 7, so that's going to be 3 times 7, which is 21. Now let's consider the y-coordinate of the image. So that's going to be 3 times the y-coordinate of the object. The y-coordinate of the object is 1, so it's 3 times 1 equals 3. And now we've got what we can call A prime. The coordinates of A prime must be 21, 3. So very simple, very straightforward, and we can do that for all the other coordinates as well. So we can say that the x-coordinate for B, so x-coordinate of the image, is going to be 3 times the x-coordinate of B, which is 7, so 21 again, whereas the y-coordinate of the image is going to be 3 times, well, the y-coordinate is now 0. So it's going to be 3 times 0, which is 0, giving us B prime at 21, 0. Let's do C. So the x-coordinate of C is 8, so we've got 3 times 8, which is 24, and the y-coordinate, 3 times, well, the y-coordinate of C is 0, so we've got 0, so C prime is 24, 0. So fairly quick, but also quite laborious way of calculating the new coordinates. We've just done A, B, C, because D should be pretty obvious after we've plotted those. Let's go ahead and plot them then. So A prime is at 21, 3, so we've got 10 on our scale here, so 12, 14, 16, 18, 20, so 21 must be here, and 1, 2, 3, up. So here we've got A prime. B prime is at 21, 0, so that's down here. C prime is at 24, 0, so that's here. And you can see D prime, we don't even need to calculate, that's clearly going to be here. If we draw these together, we've got our enlarged image. Okay, so that's going to work if the origin is the centre of enlargement. But what if the origin isn't the centre of enlargement? Then we're going to have to rely on vectors. So as long as you're fairly familiar with vectors, vectors work nicely for this operation. So let's now draw a vector. In fact, let's use a round. So let's draw a vector to A from the centre of enlargement at the origin. Okay, give it an arrow to indicate its direction. Now let's call this vector V with a bold sign over the top. So vector V. How many vectors do we need to now draw to get to A prime? Well, this vector is 7 along and 1 up. So we've got 7 along, 3, 7, 1 up. We're going to draw it to there. This gives us a doubling of our vector V. Okay, and using a different colour, let's just draw in our third vector. Okay, 7 along, 1 up gets us to A prime. So that's the basic concept that we're going to use for the rest of the video. We're going to work with vectors to enlarge things, and we're going to take the vector, for example, V7, 1, so 7, 1, which we write as a column vector. If it's a scale factor of 3, which it is to get to here, we're simply going to write it like this, 3, 7, 1. So 3 times the vector 7, 1 is going to give us 21, 3, which is exactly what we've got here. So we've got 21 along and 3 up, giving us the position of the A prime point. And by doing the same operation on any of the other points, we'll easily be able to again map the image. Okay, so let's now work on a slightly altered problem. We're going to keep the scale factor, in fact let's write that down. So we're going to keep the scale factor at 3 just for the moment. So we'll have a scale factor of 3, but the centre, let's write it here, the centre now will move to, let's say, 10, let's have it down here, so 10 minus 1. But keep the scale factor at 3. So this time we can't work with the coordinates, we have to use the vector system. So let's go ahead and draw a vector. So we'll start by drawing from here to here. Draw our arrow. And if we label up our object, then we'll say this is A again, B, C, and D. So if this is a center, we'll call it M, and this vector is M to D. Okay, let's go ahead and do another vector going from M to B. Again, draw our arrow on there. And now we've got two vectors that should be enough to position our image. So we're going to scale up by a factor of 3. Okay, now this time we're going to write it out like this. So we're going to start with, let's call this problem A. We're going to start with working out where D prime is going to be. So M to D, let's first of all work out what the values are for the vector. So M to D is, well, it goes 2 to the left and 2 up. So it must be minus 2, 2. So we'll write that as 2 minus 2. Okay, now to scale it up, all we need to do is multiply by the scale factor. So we've got 3, 2 minus 2, giving us 6 minus 6. Okay. So, starting from our center of enlargement, we need to, what have I done wrong? We don't need to go to 6 minus 6, as that would take us along here. What we need to do is check where the mistake is. And that's getting this round the wrong way, so I've gone a little fast there. It was minus 2, 2, so minus 2 and positive 2 in the y direction. Okay. So minus 2, 2. Okay, that looks a bit better. We've now got minus 6 and 3 times 2 in the y direction, 6, so up 6. Write that down nicely. Minus 6, 6. Okay, so now from M we go along 6, 3, 6, and up 6, 3, 6. So here we should have D prime. Good, okay. Now, M to B is a different vector. So we'll have, oops, M to B is what? Well, you go 3 to the left, so it's minus 3, 1. So let's write this correctly this time. Minus 3 along, and then 1 in the y direction, positive 1. And again, 3 then times minus 3, 1 is going to give us 3 times minus 3, minus 9. And 3 times 1, 3. So minus 9, 3. So all we need to do now is go along 9, 3, 6, 9, and up 3, 1, 2, 3. Which gives us the B prime. So our plot at B is at 1, 2. Okay. Now again, we don't need to worry about the other vectors. Once we've got 2, even with 1 it's possible to draw it out, but once we've got 2, we can go ahead and draw in A prime, and A, B, C must be here. C prime. And then join them together. Okay. Right, let's work on another problem. So problem B, let's say we want to keep our centre of expansion, so we've got centre 10 minus 1 again. But this time I'm going to introduce fractional scale factors. So scale factor of, let's halve it this time, say 1.5. So scale factor of 1.5. So again, pretty straightforward. It's going to be 1.5 times that vector. So m to d, that should have been d prime and m prime, m to d, let's call it prime prime this time. Okay, m to d prime is going to be 1.5 scale factor times minus 2, giving us 1.5 times minus 2 is going to be minus 3, and 1.5 times 2 is 3. So nice and simple, we've got to move 3 in the negative direction, in other words to the left, and 3 up from the centre of expansion, or the centre of enlargement I should say. So there we've got our d prime prime. So d prime prime is here. Okay, now what about m to b prime prime? So we've got m to b prime prime. It's going to be derived in the same way. This time the vector is minus 3, 1. So we've got 1.5 times minus 3. We could say, in fact, if we want to just make this a little bit easier to calculate, we could say 1.5 is 3 halves. I'm just going to change that to 3 halves. And then I can just multiply the numerator by minus 3. So we've got minus 9 divided by 2. That's going to be minus 4.5. And then we've got 3 halves times 1, so that's 1.5. So again, counting from the centre of enlargement, we've got 2, 4 and a half. So that takes us to here. And then we want to go up 1.5, which will take us to here. So right in the centre of that square. So that's got to be b prime prime. And again, easy then to plot a prime prime and b c prime prime must be here. Okay, let's go ahead and join them together. Okay, now finally, problem C. What if we have the centre in the same place, but this time a true fraction? Let's have a scale factor of 1/4. So once again, we've got m to d, let's say prime 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 this time, is 1/4 of minus 2, 2. That's going to give us 1/4 of minus 2 is minus 1/2, or 0.5. And 1/4 of 2 is going to be just 0.5. Okay, so that's m to d prime prime prime. M to b prime 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 now. We calculate in the same way. This time we've got minus 3, 1. So we're going to have 1/4 of minus 3 is going to be minus 3/4, so minus 0.75. And 1/4 of 1 is, of course, 1/4. So, whoops. Let's just rub that out. So 0.25. Okay, now this is going to be a bit fiddly, but what do we need to do? Well, first of all, start from here. We go along 3/4 then of a square. So along 3/4, that's a half. 3/4 is going to be about there. And we go up just a quarter. So we go up to here. And that makes sense for B prime prime. B prime prime prime. That's B prime prime prime. Now let's look at D prime prime prime. We go along a half and up a half, and that takes us to here. And again, easy to fill in. Sorry, that's D prime prime prime. Easy to fill in the other coordinates and to see that shape very clearly. It's a quarter now of the original object. The other thing we might just want to note before we move on is that it moved not in the direction that we seem to be moving in all the other times, to the left and up, but this time it moved in the opposite direction. It moved down and to the right. So when we've got a fractional scale factor, it's going to be moving downwards in the opposite direction towards the centre of enlargement. Okay. Okay. Now, what would happen if we didn't know the centre of enlargement, but we were given a drawing? In fact, let's just produce an example like that. So here's something I prepared earlier. Let's just draw. This time what we'll do is draw a rectangle. So we've got two different dimensions instead of always a square. And now let's draw something larger but slightly awkward down here. So starting about there. Yeah, there we go. Okay, so now we've got a problem that we don't know what the scale factor is. Let's say it goes in this direction. It's enlarging, but it's getting smaller. So it's an enlargement that gets smaller. It goes in this direction. But the first thing that we don't know is the centre of enlargement. So what is the centre of enlargement? Okay, well, we've already seen that using our vector methods that we get lines from each of the vertices. So we can use a geometric method to work out where the centre of enlargement is going to be. We know it's going to be roughly here. If we take our ruler out and join these two vertices together, okay, like this, and keep going, then when I join my next two corresponding vertices together, where they cross should be the centre of enlargement. And that's because what we've seen is we enlarge this vector from here to here. So whatever that enlargement is, it must come from here. So it's kind of working backwards. So we think that our centre of enlargement has got to be, let's write it in now, has got to be at the coordinates 5 and what's this? 8. So 5, 8. But I'm just going to check that, and I can check it by drawing, picking on another vertex. So let's say this one here, and again joining it back to its corresponding vertex, and hopefully it will go through exactly the same point. Let's see if it does. Okay, so we can be certain now, pretty certain, that this is correct. And now we can work on the scale factor. So we know the centre of enlargement. Now let's work on the scale factor. Well, as I said, this is quite a tricky example. And if we were trying to work on the distances of the vectors that we would overlay here. And then those distances we could calculate by Pythagoras. Perfectly possible to do that, but it's going to be quite a difficult thing to work on. And what we've got, in fact, is proportionality. So we can use what we know about proportionality, ratios and proportion, to actually make this task a lot simpler. And what I'm going to do is take the simplest side, this side here, 2, and say, well, okay, what's the ratio of this side to its corresponding side? And that's going to be the easiest way to do that. So let's go ahead and do that now. So what we're saying is that this side, let's call it the height, let's call it H1, is where we end up after we have enlarged, carried out an enlargement on this object here. So this is H2. So let's write that down. So we've got an enlargement from, let's call this let's call this G, object G, and this object H. So when we're going from G to H, what we're doing is enlarging by a scale factor of H1 over H2. That will give us our fraction. And H1 is, well, 2 squares high, so 2 over H2, which is 5 squares high. And if we like, we can convert that to a decimal, 0.4. So we've got our centre of enlargement and we've found our scale factor. But again, I want to do a check. So let's take another side, which are much easier to work on than the diagonals. Let's take another side, and obviously what we want to do is calculate now the width. So we've got width 1 over width 2. So again, as our check, we might as well use the same colour. Our check, we're going to take width 1, put it over width 2. Width 1 is 3. What's the width of the larger rectangle? Well, 3, 7.5, so 7.5. Now that at the moment doesn't look like 2/5, but we don't want 7.5 in the denominator, so let's double both numerator and denominator so that we get 3 times 3 is 6, 7.5 times, 3 times 2 is 6, 7.5 times 2, well, that's 15. Okay, and does that simplify to 2/5? Yes, because we can divide 3 into 6 to get 2, and we could divide 15 by 3 as well to get 5. So that gives us a check of our scale factor. Okay then. Now one final problem that we're going to just explore in this video. What would happen, just erase those, what would happen if we were to enlarge by a scale factor that's negative? Now, so far we've just looked at shapes, so I'm actually going to draw, let's just get rid of this, I'm going to draw a symbol this time, so not an enclosed shape, but a series of lines. And if I draw from here to here, you can see the familiar shape of an arrow. Okay, let's label up our arrow. So if we call this A, call this B, this can be C, and this can be D. So what I'm going to try and do here is enlarge by a scale factor of -2. So let's keep it simple. So the centre of enlargement, let's call it centre of E, centre of enlargement is going to be the origin. and the scale factor is going to be this time a negative minus 2. Okay, so again we can start. I mean, there are two ways of working on this. We could work on the x coordinates of A because we're enlarging through the origin now, or we could use a vector method. What should we do? Let's start by working on the x coordinates of A. So A has an x coordinate of the x coordinate of the image of A is going to be minus 2 times, well, what's the coordinate? So it's 1. So it's minus 2 times 1, and that will give us an x coordinate for the object, an x coordinate for the image of minus 2. There we go. So the y coordinate of the image is going to be minus 2 again, so that's the scale factor, times, well, what's the y coordinate of A? 2. So minus 2 times 2, minus 4, giving us the coordinates of A prime as minus 2, 4. Minus 2, minus 4. Okay. So in other words, A prime is going to be minus 2 along and minus 4 down. So that's going to be here. Okay. So let's just label that A prime. Okay, that's done the first one. I'm going to not go through the whole of this process, but let's do one more. Let's go for B. So if A has gone to here to become A prime, where's B going to go to in relation to A? Okay, let's use the same method. So we've got the x coordinate of the image is our scale factor minus 2 times 4, because the x coordinate of B is 4, so times 4, giving us the x coordinate of the image as minus 8. Okay, the y coordinate of the image is going to be minus 2 times the y coordinate of B, which is 2. Minus 2 times 2, minus 4. So we've got B prime at minus 8, minus 4. Okay, where's that? So minus 8 is all the way along here, minus 4, B turns out to be down here. So you can see that B, to get to B prime, has moved a lot further than A to get to A prime. And I don't know if that's what you were expecting, but that's the result that we've got so far. I'm going to use a different method now for C and D, and this time we'll use the vector method then. So let's draw a vector, but this time multiply by minus 2. So what's going to happen to the vector if I draw to minus 2? Well, the vector is from the centre of enlargement is 3 to the right and 1 up. So let's draw that down straight away. The vector from the centre of enlargement to the point C is, so let's call that O to C. That vector is 3, 1. Okay. What we want though is the vector C to C prime. So how are we going to get that? Well, simply we're going to multiply 3, 1 by minus 2. So let's start with minus 2, scale factor, and then the vector 3, 1, and we get minus 2 times 3, which is minus 6. Minus 2 times 1 is 1. So, sorry, it's 2. Okay. It's 2. So what have we got? Minus 6, 2. Let's have a look. So from the centre of enlargement, we're now going to go along 6, along to the left 6, that's minus 6, and up 2. Now why up 2? Because that doesn't seem right at all. Because again there's a mistake. Minus 2 times 1 is minus 2, so minus 2. So minus 6 minus 2 is the vector, so minus 6 minus 2 takes it to the point here. So let's label that again. And that will be C prime. Let's have another go. Finally, with D, so C prime, we can go straight ahead now and write C prime, D to D prime, like that. That's going to be negative 2 times the vector to D, so that's going to be 3, 3. Give us minus 2 times 3, minus 6. Minus 2 times 3 is minus 6 again. So we should find D prime at minus 6 minus 6. So that looks about right. Okay. Now let's draw those vectors on the plan so we can actually see this operation. And the reason why I'm doing that, you don't have to do this, is that I like to see the transformation as an animation, as literally a transforming, a warping of the space. How did we then get A to A prime? How did we get this B to B prime and C to C prime and D? What we've got is a kind of crossing over. And if we draw the vector lines down over the top, we're going to see that very clearly. So let's go ahead and do that. Okay. So start with C. And now with D to D prime. Goes through here, down to here. We've got A to A prime. And finally B to B prime. So what you can see is what must have happened in this transformation is this arrow shrunk and shrunk as it became a fractional scale factor until it went to 0. It became a single point at the origin. Then when it became negative, it expanded again. But this time everything turns upside down, so flips around the other way. So if we join these together, we should find the arrow pointing in the opposite direction. Okay. Now, have a look at this diagram here. What have we got? We've got, well, let's say that this is the image, let's call it the object rather, let's call it R. And we've got 2 transformations here, one which scales up and one which is going to scale down. So let's say this is S and this is T. You should be able to deduce that the centre of enlargement, I'll just mark that on here, is at minus 2, minus 2. So there's the centre of enlargement. But I've filled in these shapes now because I want to talk just briefly at the end here about area. Let's start with R to S, the scaling up operation. So we've got a scale factor here of, well, each side is doubled, so it's a scale factor of 2. But remember that this is a linear scale factor. So if we're talking about area, so if we're asked about the area of S, for example, find the area of S, then we need to remember to square our scale factor because we're scaling up by a scale factor of 2 in 2 dimensions, 2 directions here. So the area of S must, Neat enough. There we go. Area of S must equal the scale factor of 2 squared times the area of R. The area of R is 2 times 2, which is 4. So we've got 2 squared times 4, giving us 4 times 4, 16. And it can work in the other direction as well. Make sure, if you've been told, for example, that the area of T is 1/16 of the area of R, so area of T equals 1/16 the area of R. Well, if you're asked for the scale factor of that second transformation, then be careful not to say that it's 1/16. Because what we have to do, if we're going in the opposite direction, here we were going from linear scale factor to an area, now we're going from an area scale factor to a linear. So the scale factor must equal the square root of 1/16